Hey everybody, this is Larry. This is day 13 of the Leetcode Day Challenge. Hit the like button, hit the subscribe button, join me in Discord. Let me know what you think about today's problem. Today we have 2563. Count the number of fair pairs. Given a zero index integer array nums of size n and two integers lower and upper, return the number of fair pairs. A pair ij is fair if I is less than j, okay? Lower. Okay, so I plus j is in the within the bounds of between lower and upper, right? Okay. What does this mean, right? There are really a couple of ways to think about it, really, because there are n elements, right? My apologies, excuse me. I do record these live, and today I'm starting a little bit late because I am an idiot. That's all. But just hung out. But yeah, I mean, I think the thing you can do, right, when you see these, is that okay? Well, you have all of n elements, right? Well, exactly n elements, really. And in this case, n is 10 to the fifth. So you cannot do n squared. That's way too slow. N log n is okay, or if n is even better if possible. But these are the things we're thinking about. And then the range of numbers are, pretty big, so we don't, effectively, you can think about a general, like the range of the numbers don't matter. There are rare times where, like, maybe we deal with bitwise operations or something like this. Maybe we can take advantage of the fact that there's 32 bits. But this one is probably not going to be it with addition and all these things. But yeah. So then the other thing is just thinking that, okay, well, look, you fixed one of these things, right? I and j for all matters. Like, it doesn't really matter which one is which. Of course, there is very minor difference that j is I and j and so forth. But I is less than j. But everything else is pretty much the same, right? And here, and this is something that I've been working on a little bit as well, is just using better variable names, at least for contest-y situations, right? And here, you can do, like I said, it doesn't matter which way you do it, as long as you're following along, and just thinking about which one you think it's clearer to you, or you think it's clearer to implement. And it's okay to be wrong, right? This is why you practice. This is why you're here doing the daily problems, so that you're like, oh, okay, maybe if the other way would have been faster. And of course, now that you understand yourself slightly more during contests, you'll be that much faster. And for me, the reason why I choose j over I mean, you have to iterate either one of them, so it doesn't really matter per se. But the reason I chose j is, and like I said, it's the same. But for j, if I go from 0 to n, then everything that I processed previously is going to be I, and I can just keep going, right? So okay, so technically this is for j. It's a little bit awkward then, because here we have two things we want to do. We want to look count for i's that matches, right? Fair enough, right? And then now we process j as an I for the future. I don't know if this I feel like this step I always kind of been still playing around with how to explain it, honestly. So, but basically the idea here is that, okay, well, everything that we processed previously, because we have this 0 is less than I, or sorry, yeah, I mean, I is less than j is the more important part. I mean, obviously it's between 0 and n, but I is less than j, so everything that we previously processed is going to be I. So then we look for i's and j's that match. That part I hope makes sense. And then now this j becomes an I for future j's, right? Because now that we've done with j, now it is an I for future j. So you not pre-process, just regular process them. So that's how the algorithm goes. And of course, you can't really avoid this loop. I mean, it's going to be either I or j, but it doesn't matter. But still an O of n loop, O of, an n iteration loop. And then here, that just means that the rest, this has to be either log n, and this has to be, the worst is that, or the longest that you can take will be log n for either one. And yeah. And here we can just kind of figure out, right? So it doesn't really matter. We could look at it one at a time. So numbers of j, we have, we have this formula, right? We know what nums of j is. We're looking for this formula, we're solving for num sub I, right? And here you can just subtract num sub I from technically you could rewrite this as 2 equations if that makes you think of it a little bit easier, right? Something like this, right? And then now we subtract num sub I on both sides. You have lower minus num sub I is less than or equal to num sub j, and also num sub j is less than or equal to upper minus num sub I, right? Or you can just say num sub j is in between upper of num sub I, lower minus num sub j. I think I messed this up actually, my fault. I mean, okay, I mean this is fine, but yeah, you're looking for this. You know this, so this is not useful. I kind of messed up. I was a little bit lazy and I kind of went a little bit fast. Actually, what you want to do is subtract num sub j from both sides, right? Sorry, friends, it happens, right? So then you have num sub I is equal less than or equal to this. Subtract num sub j from num sub j from both sides. You have this, right? And then now you have what we're looking for. Okay, this is a constant, or I guess technically they're variables, but the inputs, they don't change, right? In the moment, they do not change. We have num sub I, which is what we're looking for, and then yeah, and then it is, and this part again is constant it is an invariant for the part of this loop because we're already given j for this part, and of course upper whatever. And then now all we have to do is look for num sub I and or num sub I that fits this case, right? And that's really the idea for the look for the i's and j's that match. So let's just say we have total for total count. I'm a little bit lazy. Indexing is always a little bit tricky for me, so you know, we'll see if I get it right this time. But we do a binary search because I lied. Okay, well, I mean, I think the reason why I'm a little bit slow is that I'm trying to kind of explain this part independently from this part, but it's hard to kind of do that, but because they kind of work together in concert, right? But the idea here is just, well, what is the best way to kind of, you know, so you have the numbers that you've seen before. Let's just say, you know, I like to imagine a number in the middle, say this one. I go, okay, well, now I know that all these are possible i's. What can I do to make it easier to search for the ones that we want? In this case, that means keeping it sorted in a binary search tree or some kind of data structure like that on the left side, and then do a binary search on them. So here in Python, we're going to have sorted list. Maybe I don't know. I wonder if you can just pre-process some things. I think this is a fine way of doing it, honestly. And the idea here is just that, well, okay, you put everything in a sorted list, you pass order j, and then it gives you the indexes, and then the indexes will let you, you know, do some count about number of entries that are inside, and then you can process it by just adding num sub j into the sorted list. And like I said, that'll be fine. We can even probably finish it, but I think one thing that I just noticed, and some of this is experience, maybe it's not because it took me a while, but I just noticed that for this problem, the order of operations nothing really matters, right? The i's and j's don't matter. What I mean for this problem is that for I and j, like the way that we did it, we would have to put in a sorted list or a binary search tree type data structure in either C++ or Java or something like this, and it's fine, right? The search is log n, search is log n, we process is also log n. It's fine, right? Fine answer, you know. But I think the thing is that what I was wanting to say is that I and j are actually like, there's nothing about this constraint that is order dependent. So first of all, right, is that there is this everything is only pairwise, right? Meaning that it's not like a subarray or subsequence or something like that. It's only a pairwise thing. And what I mean by that is that because and additionally, to be clear, addition is what's it called? Which is commutative, right? A plus B is equal to B plus A, right? And then as a result, the ordering really doesn't matter, right? And why I'm making a point of this is that, and some of it I'm still trying to double check in my head the proof, but the idea here is then actually, you know, we can do what we said, but we can actually just sort the input, right, as a result. And as you can see, this is not my first idea, honestly. I just kind of noticed this right now, right? And yeah, and the reason why you can sort it, and I hope I'm right, because if I'm wrong, then, well, I mean, we still have another way to do it, so I'm not that worried. But as a little bit of an upsell on the algorithmic side, you can sort it because if you look at every, like if you do an n square kind of way of doing this, then and look at every I and every j, the ordering really doesn't matter, right? Because it's either, or maybe another way of saying it is that, okay, well, a pair ij is fair if this thing, but that means that if, as long as you count one pair once, it doesn't matter if I is j or j is less than I, as long as you don't kind of do things in a weird way. So I think if you do sorting, it should be okay. I think the only thing that's tricky is double counting. No, that's fine. No. You still do it. I mean, yeah, no. I mean, I think, yeah. There's no double counting if you do it carefully. Yeah, that's right. I was being a little bit sloppy in my head coding before actually coding. No, but yeah, it should be fine. But basically, the idea is that after this sort, we still do the same thing, right? We just look for j's and i's that match, and then we kind of just do it this way. But except for now, instead of having to, instead of processing stop, because before we have to do something like sorted list dot add num sub j or something like this, and that's fine. This is log n, right? But actually, we don't even have to do that anymore because we know that when we insert the new num sub j, it is going to be the biggest element in the new list, kind of. So then now, all we're doing is binary searching on this number on the prefix before j, and that's really it. You have to be a little bit careful because you're not, because if you do the sort list way or binary search tree way, you insert as you go, so you don't have to worry about off by ones and stuff like this because everything is inserted afterwards. So you kind of, it's just a little bit easy to be careful, or like kind of like an inherent safeguard. But if you do it this way, you have to make sure that your indexes doesn't go beyond, right? So okay, so index left, we have nums. We want lower minus num sub j, right? And then left index is equal to this, right index is equal to bisect dot bisect. I'm always I always have to be a little bit careful whether using bisect left and bisect right on this one. Also, maybe I have to double check. Well, in any case, you can kind of subtract these things out, or not subtract, but just take these things out to be to two different cases, right? So here, how many numbers are for this is true? Because I think I've double checked to make sure that and that would allow me to figure out whether it's bisect left or bisect right, and what to do with these, right? So what I want is, so we're given this number. We want the first number that is greater than or equal to it. So this is bisect left, right? And then here, this is this one. So let me. And then this one is for this one. Right? And then now, if it's equal to, So we want to do bisect something of nums, this thing, right? And now if it's equal to, what do we want? We want bisect left, because if it's equal, we don't want it to be included, right? We want everything to the left of the index if it's the same. Oh no, that's not true. If it's the same, it is good. So we want bisect right, because then now this will give you the index of the number that's strictly greater than it, and then you can keep everything from the left. So you just have to be kind of to talk yourself through it. As you can see, even it's not. With practice, you probably could have like a good intuition, but still, I feel like I make too many silly mistakes on this, so I try to slow it down, right? And some of it is just But yeah, okay. So that means that, so then now it means that, let me add in some additional comments. L index minus 1 outside the range. So maybe another way of putting it, Lx is inside the range, inclusive. And then here, R index is outside the range, right? Outside the range. And that's, yeah. So then now we can do something like total, R index minus left index. I think that's right. And then now we process J by sweeping. Actually, one thing that I messed up, and I was talking about it, but then luckily we get to process J, is that R index cannot be graded or even equal to J for double counting purposes. So then now this is going to be at most min of this and J minus 1 to kind of keep it. Though actually we want this to be exclusive, so actually it'll be J, right? So because this formula is exclusive, otherwise you have a plus 1. It's either that or I messed up anyway. I mean, it's very easy to mess up, but that's kind of, I think the idea is right. Right, so yeah. Alright, well, oh no. Well, -8 is probably not right. Did I mess up the index? I mean, we definitely can do, do this. I think it's possible that when you do a binary search, this number, this number shouldn't be whatever, but I guess because of the min thing, this can be negative, and that's why I have to add this. I just kind of forgot. I mean, as you can see, it was a very easy fix. But am I confident enough this? Honestly, not really. It's very, for Larry, for me, I am Larry. It's very easy to be off by ones, but if it was a contest, I probably would play around a little bit more. Today I'm a little bit lazy, so let's kind of give it a free spin. Hopefully we're good, and yes, we are. Nice. But yeah, that's really the idea. I think the sorted list thing, I wonder if I did a sorted list previously. Oh no, I didn't. Man, this thing is cray. I don't know. I mean, oh, I see. I mean, I guess that's the other way of doing it. I was like, I don't get how to... But the other way of doing it, of course, is just knowing that you're going to double count and then divide it by 2. But the only thing that is tricky is that if itself is inside the range. I actually thought about this while doing it today, but I was like, that's a little bit tricky maybe. But that's what I did last time apparently. But this is basically saying that we're going to double count it, but we don't double. We have to take out the count where you have a plus a or something like num sub I plus num sub I or something like this, which if you're a little bit sloppy you can do. So okay, I mean, yeah, I mean obviously equivalent, but that's how it goes. I guess I didn't do. I thought I would have done sorted list before. I didn't even remember this problem, but yeah. I think it is kind of cute to realize the sorting thing, but otherwise everything is O of n number of iterations. Obviously n log n, log n, log n. So this is going to be n log n. And that's pretty much it. That's all I have for this one. Let me know what you think. Thanks for watching. Stay good, stay healthy, do good mental health. I'll see y'all later and take care. Bye bye.